Okay, if you've been watching the previous videos, you know that in the past you've seen this diagram where we have a car moving 60 miles an hour. It doesn't go any other speed. It's represented by this red vector. We had a coordinate system that showed north and east, just like a map. And we laid our vector on there because the car is always going 60 miles an hour. It can be going north, east, or anywhere along this line. This vector can rotate, and you can be going some combination of north and east. So all of that's pretty simple, and we're going to now apply that to space-time. We're just going to change things around a little bit, and there we go. Now, instead of our car going 60 miles an hour, we have a spaceship that I'm going to be in, and that spaceship is going to be going 186,000 miles per second through space-time. One thing that's very important to remember here is that every single thing that there is always moving at the speed of light. Never slower, never faster. It's always moving at the speed of light through space-time, not through space alone. Because remember, we're dealing with a four-dimensional space-time now. We have replaced our north with time, and we have replaced our east with space dimension x. Now, there are three space dimensions, so this diagram actually represents four dimensions. There's three of space, one of time. I have removed two of the space dimensions so that I can draw this on a two-dimensional screen. The red vector, again, in this case, instead of representing a car going 60 miles an hour, is going to represent me in a spaceship. However, whether I'm moving through space or not, this vector always has the same value of 186,000 miles per second. It can be moving through space, it can be moving through time, but the value is always the same. So when we were looking at our plot of north and east, the car was always going 60 miles an hour, whether you were going north, east, or northeast. In space-time, we've got the same situation. Everything there is always moving at the speed of light through space-time. You got to remember, it's through four-dimensional space it's moving that fast. And what we'll see is that we're going to see that the projections of this vector, just like in our previous videos, are going to show us how fast it's moving through space and how fast it's moving through time. So let's take a look at an example so we can get going here, because I think this will clear it up. Okay, we're going to start out very simple, where you and I are sitting across from each other, maybe at a table. We're not moving through space relative to each other. We are both moving through space-time, but we are moving through time. And since neither one of us is moving through space relative to each other, we are going to both be aging at the same rate. My red vector that represents me lies directly on top of your black vector, which represents time for you. And because of that, 1 second on your watch is also 1 second on my watch. So there's no real problem, I don't think, understanding that. It's pretty easy to see. And so we both age at the same rate. Our clocks both tick at the same rate. We're not moving through space at all relative to each other. But now let's take a look at what happens if I get in a spaceship. Here we go. I get in a spaceship and I take off, and you stay sitting in the chair at the table waiting for me. But now I'm going to be going 70% the speed of light through space. Okay? Now, I'm still going at the speed of light through space-time. This vector is the same length. But because I am now moving at 70% the speed of light, the vector has rotated to about a 45-degree angle. And at a 45-degree angle, if we take my space-time vector and we project it on your space axis, when you look at me, you see on your space axis, you see the projection of my vector on your space axis, which shows me going 70% the speed of light through space. Okay? But the fun part and the time dilation part is that when you look at your watch, you will see that 1 second that passes on your watch is different than when you look at my watch. When you look at my watch move in the moving spaceship, you will see that only 0.7 seconds have passed on my watch in the spaceship. So what has happened is by getting in the spaceship and moving through space, I have traded some of my motion through time for motion through space. So that's what it is. It's a trade-off. The faster I go through space, the slower I go through time. And the slower I go through space, the faster I will move through time. But this vector, which represents me in my spaceship, and this vector, which represents you sitting at the table, are always equal to the speed of light. What matters is when I get in my spaceship, what matters is how the projections of that vector appear on your space axis and your time axis. And that's where the time dilation effect comes from. When this vector rotates as I move faster, the projections on your space axis and the projections of your time on your time axis change. So you see something differently than I do. Let's move to another example here. I do have some notes up here for mathematicians if you want to know exactly how I calculated these numbers. There's basic trigonometry, sines and cosines. So if you want to do the math yourself, you can. This is a 45-degree angle here. Okay, let's look at another example. Here's 95% the speed of light through space. So here, I am now going at 95% the speed of light through space. Still at the speed of light through space-time. But through just space, I am now going 95% the speed of light. Now you look at your watch. You're sitting back at the table looking at me in my spaceship. And you look at your watch and you see 1 second has passed. And then you look at my watch on the spaceship and you say only 0.3 seconds have passed. So that means if you flip that logic around, that means if 1 second passes for me in my spaceship, that means 3 seconds pass for you. Or, and that applies to any units of time you might be talking about, if 1 year passes for me, 3 years pass for you. Again, for mathematicians, here we got the sines and cosines of this angle, which is actually 18.19 degrees. But that's how you get these values. Okay, let's look at an extreme example, which is 99.999999% the speed of light. We're really moving. I'm really moving. You're still sitting in your chair. But now my vector has rotated so that almost all of it projects on the space axis and very little projects on the time axis. So now when you look at your watch, you see that 1 second has passed on your watch. However, when you look at my watch, you say, whoa, only 0.00014 seconds have passed on my watch in the spaceship. That is a factor of 7,142. So that means for every second that passes for me, 7,142 seconds, or about 2 hours, pass for you. You are aging 7,142 times faster than I am. So if 1 year goes by for me, if I make a round trip in my spaceship that takes 1 year, I go out somewhere into space and come back to the planet Earth, 7,142 years will have passed on Earth, where only 1 year has passed for me, because I have traded almost all of my motion through time for motion through space. Remember, it's always a trade-off. You're always moving at the speed of light through space-time. However, depending on how fast you're moving, that affects how fast you're traveling through space or through time as separate directions in space-time, just like going north and east. There can be combinations of the two. The same is true here. So let's take a look at one last example here. And that is, what if you're actually a light beam? And this is very interesting because for a light beam is traveling through space at exactly the speed of light. And no matter who you are or what your state of motion is, light is always measured to be moving at 186,000 miles per second in a vacuum. It doesn't matter if you're moving into the beam or away from the beam. Whenever you measure that light, it'll be 186,000 miles per second. And the reason that happens is because the space and time flex and twist and distort so that you always get that measurement. And that's what we're looking at here, and that's what causes time dilation. You cannot go faster than the speed of light through space. Anything with rest mass, like you or I, like I wrote up here, you or I have rest mass, the table, the chairs, the TV set, all this stuff has rest mass. And if you try to accelerate it to the speed of light, the mass of the object will increase because there's energy being input to increase that speed. And remember, E equals mc squared. So the more energy it has, the more massive it becomes. When you get close to the speed of light, the mass starts increasing towards infinity, and it would take an infinite amount of energy input into the spaceship to get it moving at the speed of light. So you can always get closer and closer to the speed of light. You can never quite get there. But light does get there. Light does not have rest mass, and so it moves through space at 186,000 miles per second. And when I say light, I mean all electromagnetic energy. It's anything that has a waveform that includes the visible spectrum, microwaves, radio waves, X-rays, gamma rays. They all move at the speed of light through space, okay? And so because they're moving at the speed of light through space, the red vector for a light beam lies directly on the space axis. Like I said, anything with rest mass can't do that. But for a light beam, it can lay on that space axis. And here's the cool part. Time does not pass for a light beam. A light beam does not move through time. It only moves through space. At 186,000 miles per second, that light beam does not move through time. So if you could get going the speed of light, if you could get there, then you would not age at all. Of course, you wouldn't be doing anything either. But for a light beam, that's how it works. So let's take a look at a couple takeaways here real quick, because this is what time dilation is about. This is how clocks can go at different rates depending on the state of motion you're in. So let's take a quick review. You're always moving at the speed of light through space-time. Never faster or slower. In space-time, when you consider all four dimensions, you're always moving at the speed of light through them. Nothing can go faster than light through space or time. That's number 2 here. Nothing can move faster than light through space or time. You can go slower through space or time, but you can never go faster than light through space or time. But remember, you're still moving at the speed of light through space-time. And the time dilation effect occurs because the faster you move through space, the slower you move through time. The slower you move through space, the faster you move through time. So it's all a trade-off. You're trading motion in space for motion in time, or motion in time for motion in space. You can go different rates through either one of them, but if you go faster through space, you're going to go slower through time, and if you go slower through time, you're going to go faster through space, etc. I may make another video that gets into a little more detail and breaks this down a bit more, so we'll see. But for right now, you have time dilation under your belt. If you need to review the video, that might help. You can pause it and think about what's going on here. But as you can see, it's really pretty simple. You don't need tensor calculus or Lorentz transformations to understand this conceptually, and I think you probably do understand it conceptually now. Like I said, I might make another video and go into some more detail later. But for now, you've got time dilation under your belt conceptually, and if I make another video, hopefully we'll see you there. Bye for now.